What we're going to look at today is we're going to try and figure out the distance between two skew lines in the 3D world, in 3-space. I'll give you some equations. Here you go. Here's one of them. 1 minus 2t, y equals 2 plus 3t, and then z equals negative 1 plus 4t. Then we have a second line, line 2. Now, when I mention that lines are skew in 3-space, what that means is they don't have a point in common. And then additionally, they're not heading in the same direction. So these are non-parallel lines. And sort of a fun thing in the 3D world, you can have lines that don't intersect, and yet they're not parallel either. Those lines are called skew lines, and that's what we're looking at today. You can easily identify the two lines are not parallel just by looking at the direction vectors. So if we look at these two lines here, the direction vector for line 1 are these coefficients on the scalar, right? So it's negative 2, 3, 4. Call that V1, direction vector V1. Direction vector V2 for line 2 is the vector 3, negative 5, 2. Again, those coefficients there. Okay, so these lines are not heading in the same direction. They don't have a point in common. You can sort of show that quickly if you're interested by doing this. Let's pretend for the time being that they did. If they did have a point in common, that would mean that for an x value, so if they were going to cross, we could say that these x coordinates would have to be equal. So we get this equation, 1 minus 2t equals negative 3 plus 3s. And then the y values would obviously have to be equal also. So we get 2 plus 3t equals 1 minus 5s. Well, that is a system of two equations with two unknowns. So let's try and finish that, see what happens here. So we take this first equation. We get 4 minus 2t equals 3s. And then basically that means that 3s plus 2t equals 4. All right. And then let's take the second equation. We would have 2 plus 3t plus 5s equals 1, or 3t. Actually, let's put it in an order that sort of matches up. So we'll say 5s plus 3t equals, and then 1 minus 2 is negative 1. Okay, so there's a solution for that. There's an s and t that would make these two equations be true simultaneously. And if that were the case, that would mean that the two x components were equal and the two y components were equal. So we'd have a possible candidate for a point of intersection between the two lines. So let's see what happens here. Let's multiply the top by 5 and the bottom by negative 3. The top equation becomes 15s plus 10t equals 20. The bottom equation becomes negative 15s plus negative 9t equals 3. Well, this is kind of nice. So you get t equals 23. So now we know what t is. We can get s. So we'll plug into either equation. Let's say we took, so we just take this equation right here. So 15s plus 10 times 23 equals 20. So 15s plus 230 equals 20. So then we get 15s equals negative 210. Oops, 210. Let's write that the right way. And we can divide by 15 and divide by 15. Negative 14. All right, so now what we know is when t equals 23 and s is equal to negative 14, for those two values of the parameter, that the x and y coordinates of the two lines in question, line 1 and line 2, would be equal. Now, if I want to, I could go back to the equation. I could put 23 in here and here, and then I could put negative 14 here and here, and I get to see what those actual x and y coordinates are. I'm not really even interested in that. I'm just wondering, is it possible for these things to be equal? So that what I need to verify now is, if I put 23 in here, and I put negative 14 in here, will I get back the same z coordinate? Well, this is going to be negative 1 plus 4 times 23. And the question is, does that equal negative 3 plus 2 times negative 14? Well, you can tell right away they're not going to be equal, because this expression here on the right is some kind of negative number. This expression is some kind of positive number. So what does this tell us? It tells us that even though we were successful in finding a value of s and a value of t that guaranteed the x and y coordinates of both lines were going to be equal, that the same value of t and value of s did not yield a z coordinate that was equal. And therefore, these two lines do not cross at a point. So that means they're truly skew lines, because the direction vectors are not multiples of each other, which means the lines aren't parallel, and they don't cross. So our goal now is to find the distance between these two lines. That's what we're looking to do here. So let's go to a new page and start to talk about this. Okay, so here we go. All right, so in order to figure this out, we need to have a realization. And that is, if you have two skew lines in space, you have to believe the following fact, that you can think of those two lines as lying in two parallel planes. Like line 1 lies in a plane. We can call this, it lies in plane P1, and line 2 is going to lies in plane P2. So P2 is the plane that contains line 1, line 2 that is, and P1 is the plane that contains line 1. And here's the additional thing that you have to be able to convince yourself of, and that is, you can think of two such planes, P1 and P2, such that they be parallel. Okay. So that's the key. That's the key, if you have that realization. So you need to sort of pause the video and think about that for a while. All right. Well, what does that tell us? Well, if we believe that the two planes that contain the two lines are parallel, then we know we could do the following. We could find the cross product of the two direction vectors. So line 1 has a direction vector v1 equal to negative 2, 3, 4. And this line 2 has a direction vector 3, negative 5, 2. And what can we say about them? Well, if we did v1 cross v2, we would get an answer. We'd get a vector. And that vector that you get would be perpendicular to both planes that we created. And that makes sense. Line 1 is in plane 1 and line 2 is in plane 2. We said that plane 1 and plane 2 are parallel. So if I picked any vector that lied in plane 1, well, positioned into plane 1, this direction vector of line 1 in plane 1, and the direction vector of line 2 in plane 2, the cross product of those would be perpendicular to both planes. So what does that mean? It means that we can now find the equation of either plane P2 or P1. Once we have the equation of plane 2 or plane 1, we could just pick a point on the line that doesn't contain the plane we're in. So for example, we decide to find the equation of plane 1, then we can go pick a value of s, pick any value of s you want over here, plug it into this line. You'd get a point on line 2. And then we know we can use our distance point to plane formula from what we developed already. So that's going to be our plan. And so we'll start our plan, and then we'll probably finish it in another video. So just for the time being, let's see if we can get the equation of one of these planes. The cross products of the vectors come from this special determinant. Okay, and then you have 3, negative 5. Oh, it's like a reflex to put a comma there, but you don't need to. 2. Okay. So this cross product is going to be this product here. Well, it's going to be, I'll write it out in smaller pieces for you so you see it happen. It's going to be I times the determinant of its minor plus, oh sorry, not plus, but minus j times the determinant of its minor plus k times the determinant of its minor. There you go. Now you have it. All right, so we can work this out pretty quickly. This first coordinate is going to be 6, 2 times 3, minus 5 times, negative 5 times 4. So that's going to be 6 minus negative 20, which would be positive 26. Over here, you're going to have negative 4 minus 12, which would be negative 14. But then the negative j makes it positive 14. And then in the last position, we're going to have positive 10 minus 21, which would be negative 11. So this can act as the normal vector to plane 1 or plane 2. Either one you want. Doesn't matter. So, doesn't matter. I'm going to pick plane 1. Plane 1's equation has to look like this. 26 times x minus some coordinate plus 14 times y minus some coordinate minus 11 times z minus some coordinate equals 0. So when I say coordinate, what I'm asking for is I'm saying, is there a point on plane 1? Well, that's not bad at all. We go back to the equation of the lines. Line 1 is in plane 1, and we know if we just let t equal 0, then you would end up getting 1, 2, and negative 1. So 1, 2, negative 1 is a point on line 1, which is also in plane 1. So I can go down and put that here. 1, 2, and negative 1. And this is the equation of plane 1. Well, you're basically done now. Because now that you have the equation of plane 1, we need a point. Next, we need a point on plane 2. Or we could also say a point on line 2. Because that's all. Line 2 is in plane 2. So we can get that pretty quickly. We go back up to the line here. Set s equal to 0. And if you set s equal to 0, you get the point negative 3, 1, negative 3. So that's going to go here. So negative 3, 1, negative 3 is a point on that plane. And now we're ready. Our distance point to plane formula, which we learned about in a prior video, does the following. It says that the distance we want is equal to the absolute value. You need to evaluate this point on that plane and then divide by the normal vector of that plane. So in the denominator of this expression, we're going to have the normal vector of that plane, which would be this expression. Now, it's really negative 11 squared, but I'm not going to write that because the negative is going to go away anyway. And on the top, I would have to plug this point in here. So it's going to be 26 times negative 3 minus 1 plus 14 times 1 minus 2 minus 11 times negative 3 plus 1. That is the scalar quantity. When you're done, that scalar quantity will be positive and it will represent the desired distance.